The ratio test gave us a way of exploring whether or not a given series began to look like a geometric series for n large enough. The root test is going to be an additional tool we have for looking at whether or not a series becomes close enough to geometric for large n that we can guarantee it converges. Let's take a look at how this test works. If we consider the geometric series the sum from n equals 0 to infinity of a times r to the n, we know that that series is going to converge when r is less than 1, and it's going to diverge when r is greater than 1. Let's also consider the nth root of the nth term of that sequence. Let's look at the nth root of r to the n. That is clearly r, and we know once again that if r is less than 1, the series converges, and if it's greater than 1, the series diverges. So this idea of looking at the nth root of the nth term and deciding if it's bigger or smaller than 1 is exactly what lies at the heart of the root test. The root test tells us that if we take the limit as n goes to infinity of the nth root of the absolute value of the nth term, then if that limit is less than 1, the series converges absolutely. If the limit is equal to 1, we need to keep working. But if the limit is greater than 1, then we can be assured that the series diverges. We're going to start with a very simple example to demonstrate this. We'll take a series that we know converges. In fact, we're going to look at the geometric series, the sum from n equals 1 to infinity of 1 over 2 to the n. This is geometric with an r value of 1/2, so we know it converges. Let's see what the root test tells us. So we're going to examine the limit as n goes to infinity of the nth root of the nth term. Well, in this case, the nth term is just 1 over 2 to the n. So we're looking at the nth root of 1 over 2 to the n. Well, that is the same as the nth root of the entire quantity 1/2 raised to the n power, which is just 1/2. If we take the limit as n goes to infinity of 1/2, we get 1/2. Of course, that's equal to our r value in our geometric series. But more to the point, that's less than 1, which means that by the root test, this converges. One of the places where the root test can be really helpful is when your series involves terms that are complicated and raised to the nth power. Here, even applying the divergence test and taking the limit of those sequence terms as n goes to infinity can be tricky. So let's look at what happens when we use the root test. So now we're going to be taking the limit as n goes to infinity of the nth root of the absolute value of the nth term, which is n squared plus 3n plus 1, over n to the fourth minus 2n raised to the n power. Now, if you look at the graph of this, you'll see that for n large enough, the absolute value doesn't matter. That expression is positive. So we don't have to worry about the absolute value anymore. It complicates things for us. So we can rewrite this as the limit as n approaches infinity of the nth root of n squared plus 3n plus 1 over n to the fourth minus 2n to the n. And of course, the nth root and the nth power cancel each other out, which is why the root test is so helpful to us here. So we get the limit as n goes to infinity of n squared plus 3n plus 1 over n to the fourth minus 2n. We know that that limit is 0, which is less than 1. So by the root test, this converges. All right, we're going to do one more example. This time we're looking at the sum from n equals 1 to infinity of n squared over 4 to the n. We see again we've got an nth power in there, so we might suspect that the root test would be useful to us. So let's examine the limit as n goes to infinity of the nth root of the absolute value of n squared over 4 to the n. Those terms are always positive, so we don't need to worry about the absolute value. So now we have the nth root of n squared over 4 to the n. And that means we're taking the limit as n goes to infinity of n squared to the 1 over n over 4. So that is 1/4 the limit as n goes to infinity of n to the 2 over n. Now you may know something about that limit, but I'm going to work through it just in case you don't. In order to do that, we're going to rewrite n to the 2 over n as e raised to the natural log of n to the 2 over n. That trick is going to allow us to get the 2 to the n out of the exponent so we can deal with it a little more efficiently. So we've got 1/4 the limit as n approaches infinity of e to the 2 over n times the natural log of n. I'm now going to use the continuity of the exponential function to rewrite this as e raised to the limit as n approaches infinity of 2 over n to ln n. Now we're going to look at this limit on its own. So everything I'm doing now is to solve that limit in that purple box. So we have the limit as n goes to infinity of 2 over n times ln n, which is of course going to be 0 times infinity. So we're going to rewrite it as the limit as n approaches infinity of the natural log of n over 1 over 2 over n, which we can just flip that over and get n over 2. Now we're in the infinity over infinity case, so even though we're dealing with sequences here, we can apply L'Hopital's rule to get 1 over n over 1/2, which is the limit as n approaches infinity of 2 over n, which is of course 0. That 0 is going to make its way back over here. And we can see that the limit we started with using the root test is going to be 1/4 times e to the 0, which is 1, which is 1/4. That is less than 1, and so we conclude that our series converges. Now, you may be thinking to yourself, that feels like it might have been easier with the ratio test. I think you're not wrong. Let's look at this with the ratio test. In that case, we're going to take the limit as n goes to infinity of the absolute value of the n plus first term, so n plus 1 squared over 4 to the n plus 1, over the nth term, n squared over 4 to the n. The absolute value, again, is not relevant because everything is positive in this case, so we have the limit as n goes to infinity of n plus 1 squared over 4 to the n plus 1 times 4 to the n over n squared. So that's the limit as n goes to infinity of n squared plus 2n plus 1 over 4n squared, because of course these cancel. We get a 4 left over there, and that is once again going to be 1/4, which is less than 1, and this converges by the ratio test as well. It makes sense that they both are giving us the same answer for the limit as well as the same answer for convergence, because both are measuring whether or not our sequence looks geometric for large values of n, and we see that it does. Okay, so in this video, we saw that, like the ratio test, the root test gives us a way to measure, to some extent, the geometricness, I made up that word, of a series. And we're going to do it by looking at the limit as n goes to infinity of the nth root of the nth term. We'll see that if that limit is less than 1, we have absolute convergence. If the limit is equal to 1, the test is inconclusive and we need to find another way to consider our convergence question. And if the limit is greater than 1, then we are assured that our series diverges.